So we've discussed scheduling when it applies to uniprocessor systems which are multi-program, and we've also discussed how that may differ for systems with multiple processors. In this video, we are going to introduce the groundwork for discussing a third type of system, which is called real-time operating systems. As far as recall, we only need you to keep in mind the basics of scheduling that we've already discussed. So what is a real-time system? A real-time system is one in which we introduce the concept of a deadline for tasks. When we've been discussing processes and tasks so far, we haven't considered the idea that that process needs to finish by a certain time. And when we've discussed the pros and cons of various scheduling methods and the effectiveness of those scheduling methods, we've been concerned primarily with roughly how long it takes to complete tasks on average, not when those tasks actually individually finish. With a real-time system, the key element is instead on a deadline that each task may have, or multiple deadlines that tasks may have, and our ability to meet those deadlines. When we discuss a real-time system, scheduling becomes incredibly important, and it can be argued that for a real-time system, the operating system, and in particular the scheduler, is arguably the most important. Now, there's listed here on this slide a few examples that you can read through if you like, but basically a real-time system will commonly occur in any system which has to interact with the real world in a time-dependent manner. Some further factors. The correctness of our system is no longer just dependent on the logical result of our computation, but it will also depend on the time at which those results are produced. So the processing must happen in a reasonable, timely fashion, and this can both mean that the processing must not happen too late, but also that the processing doesn't happen too early. If processing to calculate some aspect of certain results happens before some of the results are ready, then that will not have met the appropriate correctness of our system. In the next few slides, we're going to distinguish between two broad types of real-time system that we will talk about, and those are hard and soft real-time systems. A hard real-time system is the most strict version. So in this case, we must always meet all deadlines. So we have time guarantees. We must guarantee in any situation that the application is launched complete in time, and failure is often associated with incredibly large damage or fatal errors. So examples are an autopilot landing system. If it doesn't react to a side wind, for instance, within a few milliseconds, an accident involving the loss of lives of many people may occur. An airbag system or an ABS system is a hard real-time system you may be familiar with, because if that doesn't react within an incredibly short time frame to certain events, then the benefit of that system and the correctness of that system is completely delayed. It doesn't matter if the airbag correctly deploys, if it correctly deploys after you've already hit the dash. The second kind of real-time system that we'll discuss is soft real-time. So in a soft real-time system, deadlines are still important. The correctness or incorrectness of a system does not just depend on its result, but also on the timely occurrence of those results. But in this case, we're not quite as stringent with meeting deadlines. So in a soft real-time system, we have to meet deadlines most of the time. And we have to get pretty close to deadlines as well. So tasks will have an associated deadline, and that is obviously desirable, but it's not absolutely mandatory. Missing it by a small margin or occasionally missing deadlines may not be the worst thing in the world. In this case, it also still makes sense to schedule and complete a task if the deadline has passed. In a hard real-time system, if the deadline has passed, there's no point trying to complete the task at all. But in a soft real-time system, under heavy load, it can still make sense to schedule tasks, even if we know that we can't finish them exactly on the deadline. So some examples might be video playback on your machine. It doesn't matter if hundreds or so frames per day are dropped, as long as on average we get frames delivered at the correct time. Car navigation might be correct as well. If your car GPS is almost always telling you correctly when to turn, but at one point it announces a little bit too late that you're supposed to turn, that might be acceptable. So something like 5 announcements per week might be an acceptable measure of failure. A washing machine might go over time a short amount every 10 or so runs. So it might take 10 seconds longer than it's supposed to on a certain cycle, once in every 10 runs, for example. And it might have another rate of larger failures. So for instance, it may be allowed to go a minute over once in every 100 runs, for example. So when we're talking about uniprocessor scheduling and multiprocessor scheduling, we had a series of properties about a task that helped us define the scheduling method. So these were the service time, how long the task was supposed to take, the arrival time, the start time, things like that. The same sort of properties are true for real-time systems, but we also have extra. So imagining a processing timeline as we normally have, we may have an arrival time. This is the same as our normal period. And a particular process may also have a service time, which is the maximum amount of compute time required for that particular process. And in particular, for a real-time system, we may have a starting deadline, which is a time at which the process has to start by. So if the process hasn't started sometime in this period here, then we've already failed to meet one deadline. And we will also almost always have a completion deadline. So if the end of the process doesn't occur by this time here, then we've failed to meet another deadline. So just to make things clear, this is what we meant when we were talking about the starting deadline. We can also talk about aspects of groups of tasks that we may have for real-time systems. So we can break them broadly up into whether they are periodic or aperiodic. So a periodic task is repeated at a regular interval. So we will see the same homogeneous tasks coming back over and over again at a regular interval. So you can just pretend that I'm actually a good artist and these times were the same, these gaps were the same length. Often we will have some sort of periodicity, so regular frequency, and usually the execution time will be the same for each period, and the arrival time will usually be the start of that period. We can also have a scenario where we have tasks which may appear arbitrarily. So we may have short bursts of tasks appearing, and then a large gap, and then another task, and then a smaller gap, and then another task arrives. And so we call this aperiodic or sporadic. So things that have to react to real-world events that don't occur at regular time frames are examples of this, like an ABS or air brake system. Airbag system. So in this video, we've given the groundwork for discussing real-time systems, which we are going to obviously expand on in the lectures. So we've covered the definition of real-time, what we mean by real-time tasks and systems, and we've distinguished between hard and soft real-time, which is an important distinction. We've also discussed the properties that a real-time system or real-time tasks might have, so these being arrival time, service time, and start and end deadlines, and there may be other properties that a real-time task will have. And we've also discussed the periodicity, so we broadly broke real-time tasks down into periodic and aperiodic tasks.